Good afternoon and welcome to this afternoon's webinar. Thank you for joining us. We are recording this session, so we'll be able to send it out to you afterwards, as well as send it out to anybody who is unable to attend today. My name is Alison Flack and I'm one of the marketing managers here at the Met Office. Today's session is aimed at raising awareness and understanding of space weather, with particular emphasis on possible impacts for aviation. We have this afternoon Simon Machin presenting. Unfortunately, Krista is unable to attend this afternoon. So Simon, who's the Met Office's business manager for space weather, will be taking the presentation today. Following the presentation, we will have some time for question and answer session. If you have any questions, please pop them into the chat and we will do our best to answer them. We have also received several questions from you during the registration process, and again, we will try our best to answer as many of these as possible. So at this stage, I will hand over to Simon. Thank you, Simon.
Good afternoon, everyone. Excuse me. My name is Simon Machin, and as Alison said, I manage the Space Weather Programme here at the Met Office. And so today, we've got this webinar where we're going to be talking about space weather with a particular focus on aviation and relevance to the aviation community. Thinking about space weather in the broad sense and the programme that we have here at the Met Office, the reason we have a space weather programme is essentially underpinned by the fact that space weather is one of the more significant risks on the National Risk Register. It's been on the National Risk Register since 2011, and as you can see in this sort of pictorial version of the 2017 version, it's one of the more significant risks, pandemic flu being the highest, and we've all learned a few lessons from that over the last year or two. The latest iteration of the National Risk Register is perhaps slightly less pleasing to the eye, but essentially space weather retains a similar position as one of the more significant risks on the National Risk Register. So on the back of that, the government has a rationale to actually provide a national space weather capability, and that's what we provide here in the Met Office, to provide a national service to support government, defence, and various sectors across industry, as well as the general public with space weather services. Now, underpinning that National Risk Register and the assessment there is what we call the reasonable worst case scenario. And the reasonable worst case scenario for space weather was developed by an independent expert group known as SEEG, the Space Environment Impact Expert Group, which advises government on matters relating to space weather. So I've just picked a few words here from the summary of space weather worst case environments, just to give you a flavour of what a really severe space weather event might mean. Longest interval of severe space weather likely to be in the order of 2 weeks. It's extremely difficult to predict the order, duration and individual space weather phenomena, but different systems could experience different impacts simultaneously, sequentially, unpredictably, and effectively randomly. It's highly likely these systems failures will interact with each other to cause cascading failure models that are fundamentally difficult to predict. So, space weather could be significant. Space weather is likely to be difficult to predict, and on different occasions and with different events, the sequence of events may well be different over different timescales. So, not a trivial issue when we come to looking at space weather. On the back of that, and again underpinning further work, we now have a series of national strategies in place, starting with the National Space Strategy, an overarching strategy that looks at UK interests in space and government ambitions for that. And then sitting under that, we have the UK Severe Space Weather Preparedness Strategy. So that's the one we're clearly focused on here at the Met Office with our Space Weather Programme. And then more recently published earlier this year, there was also the Defence Space Strategy, which again hangs underneath the National Space Strategy and with obviously a particular focus on the defence community and the assets that they're interested in. So, looking at the severe space weather preparedness strategy, there are three key pillars here. Assessment, increasing UK observation and forecasting capabilities, so obviously keyed in on what we're doing here at the Met Office, enhancing understanding of space weather impacts on industry, sectors and society. We then have the preparation pillar, increasing resilience of essential infrastructure and services and minimising the impacts of severe space weather. So here we're thinking about development of response plans and mitigation options, and then response and recovery. Ensuring the UK can respond to events effectively and recover from them quickly, with a focus here on international communication and coordination during and after events. This really with an eye on the fact that space weather isn't a localised event. It's not even a regional event, really. Space weather is usually an international event that spans great swathes of the globe, if not the whole globe at a time. Under this, the Met Office itself has a number of responsibilities to develop communication plans across government, to raise public awareness, to embed new capabilities within our Met Office Space Weather Operations Centre, to consider and work with academia to understand where new research requirements could lead to further improvements to capability, and to work with international partners on standards and communications. Now, under this, we have a strategy work plan, which includes the development of impact assessments, contingency plans, response plans, and exercising. Exercising really important to reinforce the lessons that we learn and to reinforce the validity, if you like, of those plans. And some of the key sectors are listed there, and of course, aviation being one of those. Just to think a little bit now about solar cycles and sunspots and the impact of severe space weather. Over very long time periods, solar activity does vary quite markedly. We can see here 400 years of sunspot observations, obviously not taken from modern measurements, but rather from things like tree rings and ice cores going back in time. We've had good measurement equipment for geomagnetic storms, which are the key area of interest or the key focus for forecasting, going back about 150, 160 years now. So we've got some really good records over that period. And you can see that there's a regular fluctuation in the sunspots cycle, known as the solar cycle, which runs broadly 11 years from one peak to the next. At the moment, we've just gone through a trough, through a solar minima at the end of 2019, and we're now ramping up towards the next solar maximum, which is likely to be around 2025. Now, solar minima and maxima don't necessarily mean there will be or won't be those very significant severe events, but what it does mean is there'll be a greater frequency of moderate to strong space weather events around the maximum period. The last cycle, as you can see from this plot, and the last peak was somewhat lower than some of the previous ones, and anomalously so. And so that's something that's really relevant. So if I move on to my next slide, I've got here marked the maxima and minima periods of solar cycles going back to 1934. On here, I say the red areas are the max periods, the blue areas, the minimum periods, and in between we've got some blue bars marked. Those blue bars mark significant space weather storms, significant geomagnetic storms. And you can see that some of them coincide with solar maximum, but they kind of occur almost at any time within the solar cycle. But I think the notable thing here, and probably one of the key takeaways, is that since 2005, there are no blue bars. We've been through an anomalously low period of solar activity. And as such, and in consideration of the fact that our reliance on modern technologies has ramped up and increased so much over the last 15 years or so, there's a real danger here that we may have been lulled into a false sense of security. The new solar cycle that we're moving into is showing signs that it's likely to be more active, and certainly at the stage we're at, it's more active than the previous cycle. So thoughts around resilience and the fact that the last solar cycle was anomalously low are driving some of the risk assessment that's being done now. And that's worth considering if you say, go away and think, well, space weather hasn't really troubled me for the last 15 years. I've been flying aircraft, operating within the airline industry. Well, that might just be because the sun's been anomalously quiet, and we don't want to get caught out, of course. So, okay, so let's start talking now about the specifics of space weather and what it really is. So, space weather and the work that we do at the Met Office revolves largely around the monitoring of the sun. And there are three key types of event that we're monitoring for. They're all driven really by magnetism and the sun's complex magnetic field, and the connection and reconnection of magnetic field close to active regions of the sun. And when we're talking about active regions, by and large, we're talking about areas of sunspots. And the greater the complexity of those areas of sunspots, and to some extent the greater the region, the greater the size of them, then the greater the risk of more significant space weather. The sorts of events that can be driven by these magnetic breakages are things like solar flares. This is electromagnetic radiation that travels at the speed of light. So we can't see a solar flare lift off from the sun and predict when it will arrive at Earth, because of course by the time we've seen it, it's already here and it's already having an effect. So we can predict solar flares only by observing the sun, observing the active regions on the sun, and producing a probabilistic forecast of solar flares of particular magnitude based upon the complexity of those active regions. The same really goes for solar radiation storms. They can travel very fast and again, very close to the speed of light. Can take from around 15 to 20 minutes to get sun to Earth to a few hours on some occasions. We can't actually observe these lifting off the sun. We can sense them when they get to spacecraft that are stationed at the Lagrange 1 point, which is around 1 million miles above the Earth, if you like, on the Sun-Earth line, which can give us a few minutes notice, but it is only a few minutes notice. So any warnings of these will be very short, shortly before the event actually occurs. We can, of course, sense these when they do arrive, both at the Lagrange spacecraft and when they reach us on the Earth through ground-based measurements. So again, with radiation storms, we're looking at producing probabilistic forecasts based on the complexity of those active regions. Geomagnetic storms are something different. Geomagnetic storms are driven by what we call coronal mass ejections, and these are areas of plasma, vast areas of plasma, billions of tons of material that get cast off by the sun, and these travel much slower. It's still pretty quick in the great scheme of things. We're talking about thousands of kilometers per second, but nonetheless, typically take something like 2 or 3 days to get sun to Earth, and on occasions a little longer than that. However, the very quick ones, and probably the most impactful of these, will travel sun to Earth at a quicker speed, arriving in typically about 15 hours for the fastest. And it's the geomagnetic storms that we're most concerned about. They produce a whole range of impacts and likely to lead to severe space weather. So again, to focus in on the sorts of impacts that we can expect associated with these. So solar flares affect the sunlit part of the Earth. That's because they cause ionization in the ionosphere, and it's the interaction of X-ray and UAV radiation with the atmosphere that cause the problems here. This can affect all kinds of lower frequency communication and navigation from VLF through to HF. And in the case of HF, which I know is used for aviation and particularly across high latitudes and the oceans. It can lead to blackout of HF communications. Satellite communication can also be interfered with and potentially lost in a severe case. Radars can experience interference. Satellites in orbit, in low Earth orbit, can experience orbital decay, which can lead to early re-entry of satellites and satellites not being in the expected position. Can also lead to geolocation errors, and here we're talking about GNSS systems, and it can lead to degradation of the accuracy of geolocation. Solar radiation storms, these are highly energetic charged particles, mostly protons and electrons and heavy ions. As I say, they can arrive sun to earth in a few minutes, more typically maybe an hour or two. The effects of these can lead to satellite disorientation, and you can see an example of that actually in the images playing. On the top image, we can see a NASA stereo satellite, which affected by a radiation storm essentially loses access to its star tracker mechanism and goes into an uncontrolled role for a number of hours. The effects can lead to damage to spacecraft. You can see on the lower image, the blue image there, a snow scene type of effect as energetic particles hit the coronagraph. These particles can penetrate components on satellites and cause damage to satellites, most especially to the solar panels that power satellites, so it can lead to loss of power availability. High altitude radiation exposure. So here we're talking about aircraft potentially flying at high altitude, which can be exposed to additional radiation. Going back a number of years, Concorde always used to fly a integrated radiation sensor on the aircraft to measure for these sorts of events, so they're aware of their exposure. And things like upsets to ground-based electronics. On occasions, very energetic particles can, through interactions in the atmosphere, lead to neutrons penetrating through the atmosphere and down to ground level. Under normal conditions, the atmosphere gives us quite a lot of protection from these, but as I say, under the most severe conditions, we can end up with neutrons penetrating down to ground level. These can cause upsets not only in avionics and issues with aviation and people flying through the atmosphere, but actually right down to ground level. So there are things to think about with ground-based command and control systems and the like as well. And then geomagnetic storms, which, as I mentioned, the very fastest probably arriving in 14, 15 hours, more typically up to 2 or 3 days. Essentially, they can cause all of the effects that I've mentioned previously. They carry with them also their own magnetic field embedded in that plasma. And when that interacts with the Earth's magnetic field, this can lead to, if you like, energization of the atmosphere and the electrojets within the atmosphere, which in turn can lead to a potential difference in the ground and lead to ground-induced currents. That's particularly of interest to people like operators of power grid systems, because those ground-induced currents, rather than running through high conductivity rocks, will much gladly run through a power grid and electrical cables. So this can cause some issues for power generators, and on occasions has led to the complete collapse of power grid in 1 or 2 locations. So for instance, in 1989, the Quebec in Canada lost power to the whole state there for around 9 hours as a result of a geomagnetic storm. Here at the Met Office, we have the MOSWOC, the Met Office Space Weather Operations Centre, and we're manned here 24/7, 365 days a year by expert space weather forecasters. We're one of a very few number of centres globally that are manned 24/7 throughout the year. We always have a forecaster on duty, and we always also have a trained space weather forecaster on another bench that looks after natural hazards. That way we have some contingency. If we did have a big space weather event, we could actually pull a forecaster across to help the space weather forecaster out. So we have some dual trained forecasters to provide that contingency within our operations centre. As I've already mentioned, we support government, we support the military, as well as critical sectors across government and industry. The sort of forecasts we produce are twice daily bulletins, general forecasts, providing probabilistic forecasts, as well as alerts and warnings, specific sector forecasts and web pages, and we're part of the Pegasus Consortium, which provides services through ICAO, and the role the Met Office plays here is part of, as part of that consortium, we provide a resilient backup role. That service is fronted up by FMI in Finland, but as a consortium of 7 different nations contribute to that. Some of the key documentation relevant to aviation we've got highlighted here. ICAO Annex 3, Met Service for International Air Navigation. We've got the document 10100, specifically looking at space weather information in support of international air navigation. And then here in the UK, we've got the CAA CAP 1428 impact of space weather on aviation. And collectively, they give an overview and guidance on the sort of space weather services that are available through ICAO and the ways in which airlines and the airline industry might appropriately respond to those. CAP 1428, to focus on the UK, was updated last in 2020 and includes information around those ICAO space weather advisories. There's further information around space weather in general on aviation, including probability of occurrence, forecasting and observing space weather, and safety risk assessment and recommendations within that. The ICAO advisories as a service rotates between 4 global centres. So there's the Pegasus Consortium, which I've already mentioned, that the UK plays a part in, and the Met Office provides that resilient backup for. There's a US service, which is run by NOAA. There's a brand new, only just come online in the last few months, a new consortium, which is a Russia-China consortium. And then there's a further consortium that consists of Australia, Canada, France and Japan. And each of those consortia has a 2-week period that passes in rotation where they're on duty. The ICAO advisories, I suppose first and foremost, it's worth making clear that these aren't forecasts, these are impact-based, issued when thresholds are met. And there are 3 key targets areas here for those impacts. Those are GNSS, high-frequency communications, and radiation. There has been a proposal to expand this and include satellite communication as well, but as yet that's still under discussion and proposed to be included as a future iteration of those. All of those for GNSS, HF comms, radiation are issued at 2 intensity levels, moderate and severe, and these are defined in the ICAO manual. This is what it looked like. I won't talk you through these, but as I say, the internationally agreed levels at moderate and severe. And these are reviewed, I believe, at 2 yearly intervals. So there is a review process for these, and it's potentially possible that at the next review, the SATCOM thresholds might well be incorporated into that. That'll be up for consideration anyway. So to talk about the ways in which these impacts manifest, GNSS, well, The key component here is the ionosphere through which GNSS signals have to be communicated. The ionosphere plays a critical role in satellite navigation and is influenced by space weather. And so advisories here are issued when one of the parameters crosses the moderate or severe threshold. And this can be affected through both amplitude and phase scintillation. This is signal scintillation, which can lead to initially loss of precision, but potentially total loss of signal in a severe case. Solar storms, yes, can introduce changes to the ionosphere, and these can alter when it alter and introduce errors, and as I say, growing errors, depending on the severity of the event. So this leads to positioning errors. So a key issue if we have a reliance on satellite and space-based navigation systems. As regards radiation, during strong radiation storms, and I've already talked about this, energetic particles bombard the atmosphere. The secondary particles manifest as neutrons and can penetrate further down into the atmosphere and ultimately down to ground level on occasions, where they're known as ground level events. The measurements we take at ground level of neutrons can effectively be reverse engineered to understand the likely dose in aircraft if we aren't actually flying radiation sensors on those aircraft. And the impact is dependent on altitude and latitude. Even in these highly energetic events, it's the higher latitude and higher altitudes that will experience the greatest amount of radiation. Thresholds for radiation are the result of consultations with space and human health scientists. Moderate being set as an effective dose rate of 30 millisieverts per hour and severe at 80 microsieverts per hour. And then finally, HF comms. Well, again, the ionosphere is key here. Solar flares and geomagnetic storms, as well as aurora, can all cause ionospheric interference. They can cause enhancements and changes and disturbances within the ionosphere, which can lead to the absorption of high-frequency communication signals. This can happen most frequently at higher latitudes in the auroral region. We can have something called polar cap absorption, again affecting the higher latitude regions, leading to shortwave fade out. And then following storms, we can end up with what we call as post-storm depression, where actually some of the high frequency channels can be lost. So we've got a whole range of slightly different but related features here. Most often through auroral absorption, polar cap absorption and solar flare effects, it's the lower end of the spectrum that tends to be absorbed most readily, and it's only the more severe events required to actually take out the higher end of the spectrum. But the post-storm depression sort of acts in reverse and takes out the higher end of the spectrum and tends to lead to the lower end of the spectrum being more resilient. So there are some conflicting effects here that happen depending on the actual characteristics of each event. Here are some examples of the ICAO advisories. Fairly basic standard text messages that set out the kind of event, whether it's moderate or severe, and the time that the event is actually issued. In addition to the ICAO warnings at the Met Office, we also produce our own forecasts, alerts and warnings based on internationally recognised space weather scales, which were originally devised in the US by our colleagues at NOAA, and we've adapted and tailored these for the UK. These cover all ranges of geomagnetic storms, radio blackouts, X-ray flares, radiation storms, as well as things called like high energy electrons, which are particularly important for spacecraft operating in geostationary orbits, for example. We produce watches, which are long lead time messages or forecasts, if you like, for potential increases in geomagnetic activity. We issue warnings when we expect certain conditions at a particular period of time or over a period of time, and then alerts when a particular event has a threshold has been breached. Here's an example of the scale for geomagnetic storms. Each of these goes from 1 to 5, so geomagnetic goes from G1 to G5. And on here we have explanations. We've got the explanation that was originally developed for the US, but also an explanation that we have tailored for the UK. And in this case, you can see a difference there on the G4, whereas the US version would talk about impacts to their power system. In the UK, our national grid is somewhat more resilient to that level of storm, and we wouldn't see any particular risk there. Within the Met Office, we also have sector-specific pages, and we have a page that people themselves can sign up for access to that will give information specific to the aviation community, and that's tailored for use by that community. And those can be accessed through our general space weather page, general public page, where there's a link to actually sign up for an account. There's no charge for that account, but as I say, you do actually have to go through a sign-up process to get access to the aviation page. In the MOSWAT, we provide twice daily bulletins, as we mentioned, forecasts and a summary of the last 24 hours, and then the forecast goes ahead 4 days into the future. Here we forecast using probabilities, and again these are broken down into those categories of geomagnetic storm, radio blackouts, and solar radiation storms. Here's an example, this one being a plain language forecast. We have two versions of this. One is a technical version, one is a plain language version. The technical version very much aimed at those with a pretty good understanding of space weather and the terminology. The plain language one, well, as you might expect, much more plain language and largely focused around the risk assessment and those probabilistic forecasts, which we present, as you can see on the right of the screen there. Coupled with this, we always, this is sent out by email, and on the cover page, if you like, of the email, we also have a traffic light RAG chart covering different sectors, aviation being one of those. So on this example, day 1 was green and day 2 to 4 was similarly green, but there were some yellows there for satellite operators and satellite communications. If we're expecting, or if we experience a severe space weather event, then we also produce some supplementary information. Now, this is largely driven by government and for government to aid in decision making. Here we provide a summary of the current space weather situation during or ahead of a major event. And this is complementary to the routine forecast. So the routine forecast would continue, but this is additional information that would feed into government for their purposes and would be issued to suit the battle rhythm of decision makers in government. So, for example, the government may call a SAGE team to actually consider what actions to take in the face of a severe space weather event, and this is the sort of documentation we would provide to support that. From the MOSWAT, we also provide, as we've mentioned, a series of warnings and alerts, and again, through access to an account, you can sign up to receive any of these at your choosing, and again, these will be distributed by email. And the actual warnings and alerts, well, again, that we issue, here are some examples. So this is one for a solar flare of X1 magnitude and the sort of text and explanation you get with that. This is one for a solar radiation storm. and that's taken from the GOES-16 satellite, and finally one from a geomagnetic storm, this being a G4 geomagnetic storm. So there are some key differences between what we produce from the MOSWOC and what's specifically produced for ICAO. We provide a forecast and a 4-day forecast of probabilistic space weather conditions, as well as warnings and alerts when the thresholds are briefed. The ICAO advisories are only issued when the impact actually occurs. The alerts that we issue cover the full range of space weather impacts from the 3 types of space weather, although you can choose to only receive those that you feel are relevant to you, i.e. the higher magnitude alerts perhaps. The ICAO advisories warn for specific system impacts, for example GNSS degradation due to ionospheric disturbances and radiation at flight levels. The GNSS impacts are included in alerts from the Met Office, but not with the level of location detail in the ICAO advisories. So we don't currently have that capability within the Met Office to forecast radiation exposure at flight level, but we are actually onboarding a brand new computer model at the moment that will introduce that capability here. So we expect to be enhancing our own capabilities to serve the aviation community within the very near future. And with that, I say thank you very much for your attention, and I'd be very happy to field any questions. Well, in the first instance, I think we had some questions that came through in advance, so maybe shall I have a look at those to begin with?
Thank you, Simon, for your presentation. If you do have any questions, put them in the chat. And we'll do our best to answer them. You're right, we have had some questions already. First of all, it would be great if you could highlight some real-world case studies of where space weather has impacted safety or crew.
Yes. So so a couple of examples. Back in 2017, we had some significant space weather, not severe, but significant space weather, and some quite some significant solar flaring, particularly associated with that event. One of the noted events there was loss of high frequency communications, as I've mentioned during the presentation there. And a specific example was an Air France flight that was flying over the Atlantic that lost, and I believe it was on a flight from Brazil back to France, and lost all high-frequency communications for about an hour and a half on that particular occasion. And to be fair, there are numerous occasions on which loss of high-frequency communication has been noted by airlines. We've had further significant solar flares, in fact, only a few months ago, where there were shorter outages noted of up to sort of 20 minutes, half an hour on transatlantic flights. So that's a fairly regular occurrence when we get significant solar flares. Perhaps a slightly more worrying one, going back a few years now, there was an example of a Qantas flight that was flying over the Indian Ocean that had experienced a sudden loss of altitude and went into a dive. The pilot was able to correct the situation and regain control of the aircraft, but only after it had lost something like 20,000 feet of altitude. And whilst we've never been able to categorically prove that it was a space weather event, there was a significant radiation storm concurrent with that particular event, and there's this scientific opinion is that it was likely to have been triggered by an avionic upset as a result of that radiation storm. So these are the sorts of events that can occur, and that's one of the concerns actually with radiation storms, is that not only can it potentially catch people off guard because they can be rapid onset events, but they can also present pilots with a high workload very quickly, and a lot of anomalies with avionics, which could potentially confuse and potentially lead to pilots making the wrong decisions or making the inappropriate corrections to anomalies. So that's again something that we're continuing to do work on and look into with colleagues from across the industry and Department for Transport.
Somebody stated that they're particularly interested in the effect of space weather on drone GPS accuracy. Can this be addressed?
Well, as we've mentioned again, GPS accuracy can be degraded by space weather events, and it's the disturbances to the ionosphere that lead to this. As regards navigation signals, you need really 4 fixes from satellites to get an accurate fix. And there can be occasions when the ionosphere is significantly disturbed and it's impossible to get 4 good fixes. The sort of errors that can be experienced depend to some extent on the kind of GPS system that you're operating or receiver that you have, whether you're operating with a single or dual frequency system. Dual frequency systems being more resilient, but nonetheless, there are occasions when any kind of GPS system can experience significant degradation of precision. And when I'm talking about saying significant, that can be anything up to 150, 200 meter loss of precision. And if we go to the reasonable worst case scenario of a severe space weather event, then the estimate is that there could well be a total loss or near total loss of GPS service for up to 3 days. So really important. And if we're operating and reliant on autonomous vehicles of any kind, then that's something we always need to be cognizant of when we're thinking about the security and safety of those sort of operations.
Do space weather events affect 433 megahertz, 2.4 gigahertz, 5.8 gigahertz command and control frequencies commonly used by amateur and commercial drones?
Okay. So in short, the answer is yes. Space weather and the radio noise, if you like, associated with space weather can impact on all of those frequencies. In general, the higher frequencies tend to be more resilient and more resilient particularly to the sort of ionospheric effects that can degrade GPS. So if we're generally speaking, as a rule of thumb, I would say that above around 8 or 9 gigahertz, frequencies are going to be much more resilient. That isn't to say that they will always be 100% resilient, but much more resilient to space weather. Frequencies below that can be impacted by space weather, as I say, through ionospheric effects, but also through radio noise, which can act to raise the noise floor and reduce signal to noise ratio.
Thank you. We have a couple of questions on CME events. Firstly, what are implications of major CME events on humans at altitude?
The concern here is yes, with CMEs, which can carry with them energetic particles and also the radiation storms. For general public travelling on aircraft flying transatlantic, for example, if you were exposed to a significant radiation storm, even the most energetic radiation storm would probably give you no more than a typical CT scan dose of radiation. So, you know, not critical and not life-threatening in any way. However, of course, for aircrew, pilots and so on, the exposure over multiple journeys at high altitude, and particularly that exposed to those that might fly at higher latitudes and in the polar regions, then it would be wise to be monitoring radiation dose over periods of time. And if aircrew are exposed on the occasion that we get the more severe radiation storms, then of course that needs to be taken into account when judging how much more time they should be spending flying at high altitude. Perhaps one thing to add is that supersonic flight is something that's probably in the pipeline to come back again, and flights in the stratosphere, where of course atmospheric protection from radiation is somewhat less than it is in the troposphere, and therefore as we move towards higher altitude and supersonic flight again, I think radiation monitoring on aircraft is going to be really important. Again, mostly for the benefit of aircrew, but also relevant to keep an eye on that, obviously from a passenger point of view, should there be particularly vulnerable passengers on board as well.
With CMEs previously having caused blackouts in major cities, how would EGNOS be affected, and could this have a major impact on space-based navigation processes?
Well, again, thinking about the frequencies and so on, EGNOS at around 1.5 gigahertz, yes, could well be affected by space weather. In general terms, I would say EGNOS is likely to be fairly resilient to space weather, but in an extreme event, and when we might experience a lot of radio noise associated with space weather events, then certainly operations at 1.5 gigahertz could easily be impacted by space weather, and there could potentially be a total loss should we experience a severe space weather event. And if you like, evidentially, I'll probably look back to 2003 and the experience of the United States when the WAAS system, the wide area augmentation system, was completely lost during a significant space weather event there. And I should point out a space weather event that was significantly below what we would consider a reasonable worst case scenario.
Thank you. Which flight routes typically pick up the largest exposure to solar radiation?
Okay, so well, that tends to be the higher latitude and higher altitude flights. So if we're flying across the polar regions, those typically are viewed as the most exposed, but as I say, also higher altitude. So if we're flying in the stratosphere rather than the troposphere, then I would expect an increased radiation dose there. So by and large, it's high latitude and long haul flights that are most at risk.
You mentioned exercising as a key part of preparation earlier in the talk. Has there been much take up on that side of things, and how realistic and practical have they been, considering the loss of operations or capabilities needed to truly test these impacts?
Okay. So we've done quite a lot of exercising across a number of different sectors. And we've conducted a number of exercises in the UK here with the CAA and NATS, and also with including some of the key airlines based in the UK. So we have done a certain amount of exercising in the past. I think it would be a good thing to do more of that and to develop that. And in fact, in September this year, we're planning our first international, really truly international aviation space weather exercise, which is being conducted between the UK, the US and Canada. And I think that will be a really interesting event, really interesting to understand how different airlines and different authorities in those different nations might respond, whether the responses will be different, similar, how they might communicate with each other, how they might hand off to each other in a space weather event. So I think there's still a great deal to be learned, particularly on the international side of things. But I think exercising is a fantastic way to getting to the nuts and bolts of the way that decisions might be made, who might make those decisions, and to understand the critical thresholds and how to inform operating procedures from the sort of services that we provide here at the Met Office, so that we can provide useful and actionable advice.
You said that the sun has been very quiet since 2005. So how well would you envisage the forecast performance if there was a large event? Have you been able to test this?
Well, we do forecast space weather every day of the week, 24/7, as I mentioned. What we've been forecasting over more recent times is less impactive, less strong space weather events than those we experienced 15 years or so ago. But nonetheless, we do have experience of forecasting events. It's just the magnitude of those that hasn't manifested so highly over recent times. So, of course, yeah, we do forecast. It's difficult to forecast space weather, and it's particularly difficult to forecast the magnitude of events. But we've got a few years' experience here in the UK. When we're developing our forecasts, we also actively communicate with international partners, and that's really important. So we share knowledge and experience and views on the current situation every day of the week with our colleagues in the US, but also in other centres in Europe, in Finland and in Belgium, for example. So we reach out and collaborate and come to collective decisions around the likely magnitude of events that we're forecasting. And if we were forecasting particularly strong space weather, again, that really would supercharge that international outreach, and we would be talking to a lot of people to try and come to consensus over the best possible forecast and the most likely outcomes. So I suppose the answer is we do forecast all the time, and if we thought there was a risk of more significant space weather and very significant space weather, then it would be an international concern.
And on a similar theme, when do you anticipate space weather activity reaching levels that will impact aviation again?
Well, the simple answer is space weather does impact aviation already. We've had examples of X-class solar flares over the last 9 months. The first X-class flare of the new solar cycle we experienced in October last year, and there were impacts to high-frequency communications on that occasion, and there have been further significant flares since that have led to the same sort of impact. So impact to communications is happening, does happen now already at the stage we're at in the solar cycle. More significant impacts, well, yes, I think they're likely. We're heading towards solar maximum in another, say, 3 years' time, roughly speaking. And it would be really unusual if we had a second anomalously low solar maxima where we didn't see much in the way of impact. So my message to the community would be to engage with us now to help us collectively understand the sort of impacts that might be experienced, and to help you to make the best decisions you can as and when those do occur.
How much impact does the magnetic interference from a solar storm have on backup navigation items like magnetometer-based IMUs, for example?
I'm not, well, okay, hands up, I'm not familiar with that particular piece of equipment system. Well, what I will say is that if you would like to work with us to understand the possible impacts to particular systems, we're very open to that. I'm very happy to talk to you about that. I don't always know the details of the components and the technological details, or of particular systems. But as I say, we're very happy to take questions away and work with you to help answer those questions.
And finally, could you briefly explain any linkage between space weather and Earth weather?
Well, in essence, there's very little. Space weather is not going to affect whether it's cloudy, sunny, whether it's rainy or windy on any one particular day. However, there are some more subtle connections between terrestrial and space weather. So I'll mention those very briefly. One is when we get thunderstorms and lightning in particular, and those lightning or electrostatic discharges can have an effect on the ionosphere, which in turn it can interact with space weather events and create disturbances that can cause problems for GNSS or GPS or for communications. Another event is or type of effect is with gravity waves, and gravity waves within the atmosphere can again similarly affect the state of the ionosphere. So there is a bit of an interaction there, and those can be caused by weather events, but also through things like volcanic eruptions. The Tonga eruption of a few months ago caused an interesting ionospheric effect as well. So there are those sorts of interactions. And then there's over very long time scales, thinking here about climate change, there is a further interaction between climate change and the atmosphere. In one of the less publicised impacts of increased carbon dioxide is it's causing a lowering or a contraction of the atmosphere itself, a lowering of the thermosphere. This is happening over long time periods. We're talking sort of 50, 60 years plus. But nonetheless, over a long time period, that will have an impact on satellites operating in low Earth orbit and the orbital trajectories of those satellites. So there are some interactions between space weather and terrestrial weather, but perhaps not in the most obvious ways.
Thank you once again, Simon, for your presentation and for also answering as many questions as we could. I'm just aware of the time, so I think we'll leave the question and answer session there for now. We would welcome any feedback from yourselves regarding this webinar. You will see a link to a feedback survey appear in the chat. If you could take a few moments just to give some feedback on this event today, we'll be very grateful. It helps us certainly plan for future events. And talking about future events, this September we will be holding a very similar webinar on the theme of volcanic ash and its impacts on aviation. Do look out for future details on that. If you follow our Met Office Aviation LinkedIn page, you can keep up to date with events and other things that are happening. So thank you for joining us today. We will send out the recording so you can view it again if you want to. And just a quick reminder, if you can complete the feedback survey, we'll be very grateful. Finally, thanks once again to Simon for your presentation. Wishing everybody a good afternoon and goodbye.